So we have talked about the concept of dynamic equilibrium and how that relates to reactions that are at equilibrium. Okay, we discussed about the condition of equilibrium has to do with the rate of the forward and the reverse reaction being equal, and that doesn't have anything to do with what the concentrations of products and reactants will be. That fact that those concentrations are going to be controlled by your equilibrium constant. Okay, and think of your equilibrium constant as your control manager. Okay, everything depends on the equilibrium constant. Okay, and here in this particular picture that you see in the background, I mean, you look at it and you know that that's physically impossible, right? So that little mouse cannot outweigh the elephant. But when we go to the world of chemistry and we are looking into chemical equilibrium, well, everything is possible. There is no such a thing as you will always have a larger concentration of products or a larger concentration of reactants. Okay, everything depends on that equilibrium constant, and now we're going to learn where that equilibrium constant comes from. Okay, so whether we call that constant coming from the law of mass action, probably is a little inconsequential. You don't really have to remember. You just have to remember how to determine that constant, how to write the expression for that constant. And this constant is rather simple to write because it's what you have here. And so that you remember this quickly, let's put it this way. It's products over reactants. What of the products? What of the reactants? The concentrations. Okay, think of that as a snapshot that tells you the equilibrium constant will always look like that. It's going to be products over reactants. The concentration of products over the concentration of reactants. So that's how it looks. This is your equilibrium constant. Okay, and well, to understand where this comes from, because that probably it's gonna be a little relief for you. But if we have our generic equation, a plus b going to c plus d, and the coefficients are the lowercase a, b, c, and d. Okay, those are the stoichiometric factors in that reaction. So our constant is going to be products over reactants, correct? So it's going to be your concentration of C times your concentration of D divided by the concentration of A times your concentration of B. Except that, well, let's slow down here because this equilibrium constant, different from your rate law, in which you cannot determine the rate law based on the stoichiometry, except if you are working with elementary steps in mechanisms. When it comes to equilibrium constant, then you use the stoichiometry of the reaction. Okay, so use stoichiometry of reaction. Because now each one of these concentrations, we are going to raise them to the power of that coefficient. So C, you raise that to the power of C, D to the power of D, A to the power of A, and B to the power of B. Okay, so that's where that equilibrium constant comes from. You write it based on the stoichiometry of the reaction, so you are going to use the stoichiometric coefficients that you see in the reaction, and you're going to put the concentration of the products over the concentration of the reactants. So this is the normal shape of that equilibrium constant. And if we want to do this for a real reaction, so to speak, well, we can do that, right? So we have the reaction is not just A, B, C, D. we have now something that it feels a little more real. So if we want to write the equilibrium constant for this reaction, then we start with K. It's going to be a ratio, and then you start with your products, which is NO2 and O2. So you have your concentration of NO2 times your concentration of O2, and you need to pay attention to your stoichiometric coefficients. So you have 4 here with the NO2, so this is going to be raised to the power of 4. Oxygen is just 1 mole of oxygen, so it's going to be 1 here, but because it's 1, then we can actually forget about it. And last but not least is going to be the concentration of N2O5. But since we have 2 of them here, then you have to add a 2 there. Okay, and this is going to be your equilibrium constant, the expression of the equilibrium constant for that reaction. Okay, so it's rather simple to write. So if we have this one, it's not going to be different from what we just did. So it's a different reaction. The equilibrium constant might look a little bit different, but still is going to be products over reactants. What are the products? Concentration of carbon monoxide, concentration of hydrogen, 2 moles of hydrogen, so you square it, divided by the concentration of CH3OH. And it's always going to be the same thing. So one more. We have this reaction is the combustion of propane, which is pretty much the same or very similar. Actually, never mind, it's not similar. So this is another reaction, but again, so it's a constant, right? We are going to write the equilibrium constant for this particular reaction. So the only thing that we have to follow, you're going to have a ratio here. It's going to be products over reactants. Therefore, your products are CO2. So we have CO2 here, concentration of CO2. 3 moles of CO2 means you have to raise this to the power of 3. And then you have the concentration of water. 4 moles of water means you have to raise this to the power of 4. Then you have the propane, just 1 mole, so you leave it alone. No, well, there is a power there, it's 1, but you don't need to indicate it. Last but not least, we have oxygen, and you have to raise oxygen to the power of 5. This is your equilibrium constant for that particular system. Okay, so no surprises here. It's just very simple. It's just based on the stoichiometry, products over reactants every single time. Okay. So now, what does the value of K means? So what if forget about this title here, it's in the wrong place. So we have here what happens if the value of K is large. In this case, we use 1 as a cutoff. It's gonna make more sense later on. But if the value of the constant is large, really large, then it means you will have a higher concentration of products than what you have of reactants. So let's focus on this. Let's write this a little bigger here, right? K is concentration of HBr squared divided by concentration of H2 Br2. So if K is really large, it means that either the concentration of HBr, and remember HBr is the product, the concentration of HBr is very large, or the concentration of H2 Br2 is really small. Okay, the bottom line is that when K is large, then the concentration of products are larger, much larger than the concentration of reactants. Okay, and when that's the case, when you have a constant, an equilibrium constant that is really large, then normally the language that you use there is that the products are favored. Why are the products favored? Because the concentration of the products is much larger than the concentration of the reactants. Okay, so that's in terms of we are interested in the position of the equilibrium. Like in the first slide, that elephant and the mouse, in what position are they in that seesaw, right? So that's what we are trying to determine here by looking at the value of K. So first case, we have that K is much larger than 1, and that corresponds to the case in which the concentration of products is much larger than the concentration of reactants. So what happens if the concentration of, if the constant is really small? Well, it's the opposite is true. So in this case, okay, in this case, if K is really small, then in that particular case, it means that either the concentration of NO is very small, or the concentration of nitrogen and or oxygen is really large. Okay, if this is small and these are large, then the ratio that you have there is going to be a small number. Therefore, what it means is that when the constant is really small, the concentration of reactants is much larger than the concentration of products. And as such, then we say that whenever you have a constant, equilibrium constant, that is really small, then the reactants are favored. Why are the reactants favored? Because there is a larger concentration of reactants than you have of products. Okay? So this is when K is really small. Of course, the last case, which was supposed to be here, what happens when K equals 1? It might happen. When K equals 1, then you have about similar concentrations of reactants and products. And you could say that is you are right down the middle. Okay? You are in any of those cases, you are going to be on an equilibrium condition. One condition will be larger concentration of products, another condition would be larger concentration of reactants, but when K equals 1, then you have similar concentrations of reactants and products. Okay? Now think in terms of 50-50. Now, one thing that is important here to know is how you can manipulate those constants. Because sometimes you can manipulate reactions in order to calculate equilibrium constants. So we need to know how to do that, correct? So we have this reaction here, and this reaction is written in the forward direction. Therefore, if we wanted to write the equilibrium constant for this, K is going to be concentration of C, concentration of D, concentration of A, concentration of B, all raised to the power to the corresponding power according to your stoichiometric factor. So what if we want to determine what is the equilibrium constant for the reverse reaction? Okay, so the reverse reaction it's part of the system, right? So you can write the reaction in the forward direction, or you can write the reaction in the reverse direction. So if you do that, basically what you are doing is inverting the reaction. Therefore, it will look something like this: CC plus DD goes to AA plus BB. And that's an equilibrium reaction. It's just that it's written in the other direction. This is the reverse direction. And we can perfectly write an equilibrium constant for the equilibrium in the reverse direction. So K, let's call this K forward, K reverse, and this is going to be equal now. Now these are the products, A and B, according to how the reaction is written. Now A and B are the products. A, B, B over C, D, D. And when you compare these two, okay, we are comparing this expression with this expression. And what you notice there is that they are just flipped. Okay, what you have on top in the forward K is what you have at the bottom in the reverse K. So that helps you establish a relationship that tells you that the equilibrium constant for the reverse reaction is going to be equal to the reciprocal of the equilibrium constant for the forward direction. Okay, so simply put, if you invert a reaction, the equilibrium constant for that reaction is going to be the reciprocal of the initial equilibrium constant. Okay, so this is, should you memorize this? Absolutely. You need to know how to do this. Okay, so we also have the case. This is all about manipulating K. So how do we manipulate K? So the next case is what to do if you, for example, multiply that reaction by a number. And in this we have sort of a simpler reaction. So here the constant, let's call this K1. It's going to be equal to concentration of C raised to the power of C, concentration of A raised to the A, and concentration of B raised to the B. Okay, no surprises here. That is the equation that we have there. So what if we do, let's say we do times 3. So now your reaction will look like, sorry, let me put it here, 3 times your reaction, right? Now, excuse me, this is going to be 3A times A plus 3B times B that goes to 3C times C. Okay, now all of these are your coefficients, your stoichiometric coefficients for this new reaction, new so to speak. So that's what we're going to use to write the next constant. So K2, the new reaction after you multiply by 3, it's going to be C raised to the power of 3C, A raised to the power of 3A, and B raised to the power of 3B. Okay, and guess what? We can take this expression and we can say K2 is equal to C, C, A, B, B, all of that raised to the power of 3. And what do you have here inside? What is this? That's K1. This is K1. So you can simply say K2 is equal to K1 raised to the power of 3 in this particular example. So now whatever number you multiply the equation by, then the relationship between those constants is K2 equal K1 raised to the power of n. You are not supposed to do that. Okay, and what's n in this case? Whatever number you are multiplying the equation by. So you take your initial constant, equilibrium constant, and you raise it to the power of that particular number factor that you're multiplying the equation by. So this is another critical relationship that you need to know. Next case, what if we have two equations? And in this case we have AA that goes to BB, and then BB goes to CC. So for one, we have that K1 is concentration of B divided by concentration of A. And for 2, we have K2 is equal to concentration of C divided by concentration of B. Okay? But guess what? If we take these two equations, if I take AA, BB, and then BB, CC, and I add them together, B is gone. Okay? B is gone, and then we obtain AA goes to CC. If we call these 3, then K3 is equal to CC divided by AA. And look at this. If I take K1, okay, K1 is BB over AA, and I multiply it by K2 CC over BB, then you end up canceling B in those terms, and then you obtain CC over AA. So what is the fundamental relationship here? K3 is equal to K1 times K2. Okay, so the take-home message here, and yes, you have to memorize this one as well. The take-home message here is that if you add chemical equations, of course, chemical equations at equilibrium, and you want to determine what the new constant is, then you multiply the equilibrium constant. Okay, so you have two reactions, you have two constants, you want to calculate the equilibrium constant for the third reaction, and you obtain that third reaction by multiplying the constant. Okay, so what if you have to invert or you have to multiply? Well, you have to do those operations as well. Okay, it's gonna be more complicated, but if it's just adding the reactions, then you multiply the constant. The end result could be a little bit different depending on what you actually have to do to those constants. So how about this? We have this reaction. This is our constant, right? Let's change color here. So K is equal to 5.610 to the power of 5. We have this reaction, and we want to calculate what is the constant for this reaction. NH3, now let's forget about the states for a moment, that goes to 1/2 nitrogen plus 3/2 hydrogen. So what did we do here? So NH3 is a product, now it's a reactant. So number one, you inverted the reaction, okay, and let's call this K1. And number two, you had 2 moles of ammonia, now you have only 1, so you did times 1/2. Well, you can say you divided by 2, but dividing by 2 is the same thing as multiplying by 1/2. And since we are doing it in terms of multiplying by a number, remember, you're going to have to raise to certain power here. In this case, the power is going to be 1/2. So from the first step, let's call K2, since you invert the reaction. Inverting a reaction means you have to take the reciprocal of the initial constant, so this is going to be 1 over K1, so it's going to be 1 over this, okay? And then in the second step, K3, it's going to be K2 raised to the power of 1/2, but K2 is this, so K3 is going to be 1 over K1 raised to the power of 1/2, which pretty much is 1 over K to the power of 1/2. Okay, so at the very end, let's do it on here. K3 is going to be 1 over 5.610 to the power of 5, the square root of that number. And this is going to be equal to 1.3 10 to the power 10 to the negative 3. Okay. So after you do the manipulations, remember the first one was to call it 1 over K1, and the second one was to raise to the power of 1/2, whatever number you use to multiply. Okay. Now in this one, in this case, this is probably a little easier. Okay. So in this particular case, you have the reaction, and what are you doing to this reaction? Okay. So here you have COF2 as a reactant, and then you have it here as a product. Okay, so you already know that you have 1 over K somewhere, and then here you have 2 moles, and now you have 4. So step 1 was to invert, and step 2 is times 2. So here K prime is going to be 1 over K squared. Okay, I will let you do the calculation. So last case that we're gonna see here, we have these 2 reactions now, right? So what do we need to do here? We want to calculate K1 for this reaction. And this is pretty much a sort of a matching game, and there is no a specific way to do this, but you just start to searching your reactants of interest or species of interest in each one of the reactions. So if the one on top is the one that you want to produce, let's say we start trying to find methanol in the reactions. In the first one there is no methanol, there is methanol here, correct? So you need 1 mole of methane as a 1 mole of methanol as a product. Here you obtain 1 mole of methanol as a product, so you don't have to do anything to that. So you stay with your value. And then let's say you want CO2 now. Let's change color here. What about we look for CO2? Well, CO2 is here. Now you need 1 mole of CO2 as a reactant. That reaction is giving you 1 mole of CO2 as a product. So all we have to do here is invert. Okay, and once you invert it, here K2 prime is equal to 1 over K2. You just invert the reaction. That's what you have to do. And once you do that, let's invert that reaction just for the fun of it, right? So we have CO2 plus H2 that goes to CO plus H2O. Okay, so let's forget about this one for a moment. And we want to keep everything that is on the initial equation. So we want to keep CO2, so we want to keep this one. We want to keep hydrogen. We need 3 hydrogens, so there are 2 here and 1 here. You have 3 now. You want to keep the methanol. There is 1 here. And you want to keep water. There is 1 water here. Everything else has to go. So that means the carbon monoxide, we have to eliminate it. And you end up with CO2 plus 3H2 that goes to, this is an equilibrium, CH3OH plus H2O. What is the constant for that reaction? Well, what you did was to add those reactions together. So K1 in this case, it's going to be 1 over K2 times, you didn't do anything to the second equation, so times K1. Therefore, this is equal to not K1, K3. This is going to be 1.4 10 to the power of 7 divided by 10 10 to the power of 5. We cancel this with this, and that is 2. K1 is equal to 140. Okay, so this section was more about understanding where the constant comes from and how you calculate those, how you can manipulate the constants so that you can obtain different reactions from sets of reactions. Okay, pretty much like Hess's law from 170. Okay, so that's it for this section.